Hello guys, hello the people in electronics. In this video, we are going to discuss that how a voltage amplifier can be implemented using multisim. A voltage amplifier can be designed or implemented using discrete components, or it can be implemented using operational amplifier. So first of all, we should know that operational amplifier is a voltage amplifier. First, let's select a suitable operational amplifier from the library of analog components, and let's select any component randomly from this library. Let's select this one. This is AD549LH from analog devices. So let's select this one. We can see that this component has its standard inputs and outputs. So as I said that operational amplifier is a voltage amplifier. So can we use this device as it is to amplify signal voltages? The answer is no. The reason is that any voltage amplifier has a large value of its voltage gain. I mean, this voltage amplifier IC is a voltage amplifier having a large voltage gain. So if we connect signal to the input terminal of this device, and if we want to know the output voltage could exceed the power supply voltages of the amplifier. So any amplifier uh, cannot produce output voltage which is larger than its supply voltages. For instance, if the this voltage amplifier is connected to a power supply of, let's say, plus minus 12 volt DC, then the maximum voltage ideally cannot go beyond positive plus 12 volt or below minus 12 volt. I mean, but practically, the voltage peaks should also be lower than these ideal values. I mean, the voltage should not go beyond plus minus 10 volt. The voltage peaks should not go beyond plus minus 10 volt. Reason is that if we go beyond and if we touch the power supply voltages, the output voltage will be clipped and we will not be knowing if we are having the right output voltage or not. So the reason number one is that we cannot use these ICs as it is that these ICs have very large voltage gains, and those large voltages can produce output voltages which could be clipped because of the DC supply limitations. So we must reconfigure this IC or any operational amplifier such that we could have controllable gain and we could have controllable output voltage. There are two ways of configuring any operational amplifier. These two ways are configuring the operational amplifier. Let me show you a symbol of the operational amplifier, then we will talk about more about this. This is the typical symbol of any operational amplifier. You can see that it has inverting input and non-inverting input and its output. So if we have signal voltage to be applied on inverting input and then we need to ground this non-inverting terminal, so this would become a configuration of the operational amplifier to produce inverting voltage. But if we do the reverse, I mean, if we connect the signal voltage on the non-inverting terminal, then the output will be non-inverting. So in this video, in this little tutorial, we are going to use this operation amplifier in inverting configuration, and then we will produce our desired uh, amplifier. So let's do that. Okay, so we should know, and you should know from the data sheet, that what these pin numbers uh, will be having for us. So let us zoom this IC first. Go to view. Okay, so we have pin number 1, 2, 3, 4, 5, 6, 7, and 8. So if you would open the data sheet of this IC, you would notice that pin number 1 and pin number 1 will have no connection. You can verify by opening the detailed uh, report of this IC. This is the detailed report of this IC. I think you people would not be able to know, but I will explain to you. So on pin number 1, there is offset null, and pin number 1 and pin number 5 are actually having offset null. I mean, if the IC would be exhibiting, will be showing offset problem, then these two pins can be used to remove that problem. Pin number 7 would have positive supply, pin number 4 would have negative supply. Pin number 8 usually has no connection, but for this particular IC, this pin should be connected to ground. And then pin number 2 and 3 are inverting and non-inverting inputs, and then pin number 6 is the output pin. So let's connect some resistor to this IC and configure it as inverting amplifier. So I will connect, let's say, a 10k resistor to inverting input, but I would like to flip it over, as you people see usually in textbooks. So to flip this IC, just select this IC. I mean, click on this IC and press Alt plus X, Alt plus Y. Then it will flip over. Alt plus Y. I mean, you can see this option by right clicking on the IC, and you are to flip it vertically. Why do we need to flip it vertically? Because we want Non-inverting terminal go down and inverting terminal go up. Okay, so let's connect this in here, and then we will connect ground connection to non-inverting. Now we need an other resistor to be connected on. Let's select this one, 56K. Okay, the circuit configuration is complete, but we need to connect power supply as well. To connect the power supply, we can directly connect the power supply to pin number 4 and pin number 7, but we should use a trick to use power supply connection. I mean, that trick will make the schematic a bit cleaner and it will be easily manageable. So the trick is that we should go to right click on the workspace and we should go to place on schematic on page connector. So I will select this and I will connect one on pin number 4 and I will name this connector as VN, which is negative voltage, because this pin should receive negative supply connection. So click OK and then click this one. Move this name aside so that you could see it. Okay, next we need to have another connect. So right click on the workspace again and select on page connector. Name it as VP, which is positive voltage. Click on it and flip it over. So click on Alt plus Y. This is flipped and now we can connect. Okay, now we need to have power supply connection. So we will have a ground connection, then we will have two power supplies as you might have learned in your courses. These two power supplies should be connected together like this and the ground connection should go here. Okay, now this is actually VP, I mean it is positive supply, or we may call it VCC. Sorry, we cannot use this name. And this is negative supply, so just name it VNN. Next, we need to use these connectors here also. So I will copy this one. So let's take positive first, Control C, and then use it here. It should be noticed that it has created a unique name for this connector, but we are to make sure that this name and this name are same. So I will double click it and I will edit it to make it exactly the same. If you will apply and click OK. Now this name and this name are same, which is means that these two terminals are virtually connected. Likewise, I will copy this terminal and I will paste this terminal here. I will rotate it by selecting and then doing Control plus R. Edit this one. Okay, now we are done with power supply connections. Now finally we need to connect a signal source. Let's go to signal voltage sources library and select a typical AC source. Make the ground connection, and finally now we need to observe the output. So we need to connect an oscilloscope on here. So we will select the oscilloscope from the instrumentation bar, place it here and connect here, and we are going to use channel A. So the positive terminal of the channel should be connected to output terminal and this terminal should be connected to ground. Okay, now we are done. So let's click run. We can see that the circuit is running. This is the indicator that the circuit is running, and this also shows a simulation animation showing that circuit is running successfully. We need to view the output waveform. So double click the oscilloscope and here we can see the output waveform, but we are unable to see it properly. So we need to adjust time scale settings and then voltage settings. So first let's this one. I think we should increase the time. No, sorry, increase the time scale. And now we can see that the voltage waveform is properly seen in the window. Next, if you would desire, you can decrease this voltage per division settings to observe it more properly. So this is how the output voltage. Now, if you want to compare the voltage with input waveform, you should connect the channel B to input voltage, and also we should change the color of the waveform that will be observant here. To do that, you are to change the color of this wire. So just double click this wire and change the net color. Make it the blue color. Click OK, apply, and OK. Now click run circuit, and here we go. We should make bases of the two circuits equivalent. So we will change this setting, voltage per division setting to 2 volt per division, and here we go. Now you can see that when the input voltage is going towards positive peak, the output voltage is going towards negative peak. You might be unable to see the difference clearly, so you can stop it, and enough of the waveform is actually recorded in the Multisim library, where you can scroll back by clicking this button, and you can see that the waveform is recorded and you can scroll through the waveform. Now you can see that this is blue waveform is the input waveform. It is going negative but output is going positive, and if it is going positive the output is going negative. This is how an inverting amplifier can be simulated in Multisim. I mean, we can perform other analysis on the circuit as well. For example, if you need to know the what current is passing through this resistor, what current is passing through this resistor, what voltage is actually appearing on this terminal. Ideally, you should know that this voltage is 0 volts, but practically this is not zero. I mean, you can measure this voltage. And these all these things are actually DC analysis of the circuit. You then to perform that DC analysis of the circuit, you should change the signal voltage to DC voltage. Then you can do all these things. Depending upon what kind of analysis you need to perform on this circuit, you can have various other options also. So keep in touch on these videos. We will be doing all these kinds of analysis on these circuits. Thank you so much. Bye.